last time we did this example by hand for the forward Euler method, and I cannot stress enough that this is going to be on your final exam. Examples, things like this are going to be on the final exam. So if you're only interested in a grade in this course, which I hope you're not, let's say you don't care about any of this, you just want to get a good grade, do practice this stuff, okay? So next, last time we asked how are we going to turn this into a Python code, and I need to turn this into a Python code to show you where the forward Euler method fails and how it fails miserably. We asked how we could do what would we need to write a Python code for the Euler method, and we kind of discussed some ideas that we would need to pass it the initial condition, we would need to pass the routine a right-hand side, and either a time array or a time step size, delta t, which was what we called delta t, and an end simulation time. I really like the latter, and that's what we're going to do together. So what we're going to do next is program this forward Euler method, write our own routine, and solve the lobster example. So far, we did the lobster example with the two right-hand sides, remember, one for baking it in the oven, one for boiling it. We did those with ODE int. Right now, we're going to try to solve those with our own implementation of the forward Euler method. So we'll do two things. We'll implement the forward Euler method together, and then we call the right-hand side and solve and compare to ODE int. Yes? So, no. So ODE int is your go-to time integrator. There's no forward Euler or backward Euler or Crank-Nicholson. All of these are methods that we will see a couple of them in the next few slides. But ODE int is your go-to method. It does internally, it can switch between forward Euler, backward Euler, or any other methods. So it finds the most accurate and the most stable. So, and with a footnote on that, I wouldn't say, there are so many parameters for ODE int. That's up to you to figure out kind of how much accuracy you want. But at least right now, it gets you to solve ODEs, okay? So inside ODE int is some version of forward Euler, some version of a few other methods that are optimized for accuracy and stability, okay? But if you want control over exactly what you want, then you have to implement your own routines, okay? All right, so let's go ahead, open up your Jupyter notebooks for the lobster example. Let's see, last time. Okay, so this is what we did last time, right? So we had this guy, so just open it. And you might have different initial conditions for temperature, et cetera. That's not an issue, okay? So let me add a few cells over here so I can center this. All right. And my objective here is to write a forward Euler routine. I'm just going to call it def forward Euler, okay? And like I said, there are numerous ways that you might want to implement this routine. For what we want to do right now, we need to pass a right-hand side, an initial condition for the function. I'm going to call that f0, an end simulation time, okay, assumed to be in seconds, and a time step size. This is delta t. With ODE int, if you remember, we passed a time array instead of instead of a time step and t end, okay? Why? Because for ODE int, like I just was telling your colleague, internally ODE int can take multiple subsequent time steps so that it optimizes for stability and doesn't crash the solution, okay? Whereas with the forward Euler method, we don't have that luxury. We are stuck with a fixed time step anyway, unless you want to implement adaptive time stepping, which is beyond what we want to study here. But I need this delta t over here to illustrate a point a little bit later in about 10 minutes, okay? So we need to implement it this way. So here's what we're going to do. First, we're going to estimate the number of time steps needed, okay, the number of time steps that I need to solve this problem, okay? And that number of time steps, I can estimate it by taking t end over delta t, right? So if I divide t end by delta t and make it an integer, it gives me an idea of how many time steps I'm going to need to get to t end using this delta t. So if t end was 1 second and delta t was 0.5, then this would be 2 steps, right, to get to 1 second. If delta t was 0.25, give me 4 steps, etc. Then my solution, or result, we used to call it, okay, is going to be a numpy.zeros array of size and steps, right? So that's the benefit of getting this n steps. It also allows you to create an array for all the answers, right, for your ODE over time. Okay? Then, oops. Now, for the initial condition, I'm just going to go ahead and initialize, put the first entry in my result, right? It's the initial condition, right? Because if I solve this correctly, my result is going to start at that initial condition. So I'm going to seed that first entry with the initial condition. And next, I'm going to do an internal time array, okay? So I'm going to do a linspace. I'll explain why I need that in a minute. Going from 0 to t end with n steps, okay? So what we're going to do here, we're going to create a time array. These are the times at which we are trying to find the solution for this ODE, right? So that's going to be phi at t0, phi at t1, phi at t2, and so on, right? Now we can do the forward Euler method. We're going to loop over time for n in numpy dot. We can do range for n in range from 0 to n steps minus 1. Then we can do result n plus 1 is equal result at n plus delta t times the right-hand side. Okay. Now we're going to call the right-hand side. Let me make one little change here for simpler typing. Instead of result, I'm going to call it f. Okay. Let's just call it f. Okay. Let's just call it f. It's simpler. So now we're going to call right-hand side. If you remember when we wrote the ODE, we said phi n plus 1 is equal to phi n plus delta t times right-hand side at tn and phi n. So now we're going to call the right-hand side at tn and phi n. Okay? Now, because we implemented our right-hand sides, not t, phi, we implemented them right-hand side, phi as the first argument and t as the second argument. So we'll just pay attention to that. So we're going to pass phi n first, which is f at n, and t at n. Now, that's the benefit also of having this time array. So let me call it just time at n. And I'm going to return two things, the time array and the solution. That's one incarnation of the forward Euler method. Very simple one, but it gets the job done. Takes a right-hand side function, initial condition, and simulation time, assuming you're starting from 0, and a time step size, creates a time interval, okay? Initializes a solution array, sets the first point as the initial condition, and then loops over the time steps, starting with the first time step at t0, right? You estimate phi at n plus 1, and using all information at n, and move forward. Okay? All right. So now we're going to try to apply this to the initial conditions to the conditions that we had for the lobster. We're going to apply it to both the boiling and the baking. And we got all the parameters set up already. So if we were to run these here again, so we should be able to just call the forward Euler method. Let's give it to t end. Let's declare t end equal. So let's do 60 minutes. I think we already declared t end. We already declared t end, 60 minutes times 60 seconds, right? Because time is in seconds in this case, and we already have t0. So we have t end, okay? And we're going to do, okay, we're just going to, for the convection case, for the boiling, T boiling is equal to forward Euler. We're going to give it right-hand side boiling, right? That's the ODE for the boiling of the lobster or the eggplant or the zucchini, whatever, okay? The initial condition is already T0, which we already set up over here. That's T0, okay? Then we need an end time, which is T end, which we already created, and we need a delta T. Now here's the challenge. What was nice about ODE int, you didn't care about delta T, because internally, ODE int is a huge library. Okay, it sits on top of a Fortran library that does a lot of advanced stuff. Okay, it will take you years to study that, but it does it all behind the scenes. You didn't have to worry about any delta T size, this delta T size. When you're doing your own routines, you have to worry about that. So how do you choose that time step? That's a problem, actually. And I'm trying to set up the issue now that time step selection, this delta T, is a big issue. In general, your delta T, the size of your delta T, needs to be faster than the fastest time scale in your problem. So suppose you're doing some kind of chemical reaction. You have two reactions. One of them occurs at the millisecond, and another one occurs within seconds, 1 second or 2 seconds. To be able to capture that system, your time step size needs to be at the smallest or the fastest time scale in the problem, which is the millisecond. So in the lobster problem, how do you know what that time scale is? Well, it's kind of a intuition and experiment looking at data. Now, we know for the lobster, the cooking is happening kind of pretty slowly, right? So really, the time scale could be a minute when interesting things start happening, or even 10 minutes, or 10 seconds, or 15 seconds, right? I wouldn't pick 1 hour for my time step. Okay, that's too big. A lot, some change has happened between here and here, right? So roughly, I would say maybe we could pick, a time step of 1 second if we want, or 10 seconds. Clearly, the smaller the time step, you're going to get better resolution, okay? But you're going to pay more cost because you're solving more, you have more time steps, okay? So let's pick a delta T in this case, and I know this will work. We'll just pick a delta T, let's say equal 10 seconds, okay? This is T boiling. That's the answer for T boiling. But forward Euler, now if you execute this, it's going to crash, probably. It didn't crash. OK, so this forward Euler returns two things. Returns time and the solution. We stored them all in one variable, T boiling. So let's instead store them in two variables, time and T boiling. So that gives us the forward Euler solution for boiling. And we do another one for baking, and that's forward Euler, RHS baking, T0, T end, same delta T. Now we can plot the two, time T boiling. Okay, so let's choose the same styles we chose here. Time over 60, actually, yep, we use the same values. Oh, look at that. That's our own routine. That's our own routine. It produced an indistinguishable answer from ODE int. Is there an error? Yeah, definitely, because ODE int is probably doing some extra acrobatics behind the scenes. It might be a little more accurate at some points, okay? But look, with a very simple method like forward Euler, we were able to capture this solution. Okay, so now as you start taking larger time steps, your solution is going to start becoming less and less accurate. Now I'm taking 1,000 seconds. Look at that. It still didn't crash, but we took a time step of 1,000 seconds, so it didn't capture anything between 0 and 30 minutes, right? Because there is a curve over here. Instead, it just kind of solved for a point here, a point there, point over there, right? In some cases, in the next example we're going to do, 2 examples from next, we're going to see that it's going to absolutely crash. The solution is just going to crash. Okay? Okay. Now, what do you do in your engineering classes? You use ODE int. Okay, guys? Don't worry about the forward Euler method. But there might be a time where ODE int is even not working, and you have to implement your own method. So you could start here with forward Euler. Okay? You all got it? Hoping? Yes.
I don't understand what it's saying that both my x and y data aren't in the same
Yeah,
dimension.
so let's see what you're doing.
Oh, do I have to do
Yeah, you have to split boiling. So forward Euler returns 2 things,
Oh,
right?
So
You need to, yeah, so you
here
need,
I'm going to put 2.
no, so I would just add time, comma, T boiling, time, comma, T boiling, right?
I don't even know what it gave me. I'm not going to lie. Something horrible has happened.
Oh, yeah, that's very, very
just
strange. I'm not going to read your comments left, but
I don't know what happened.
time,
I
T
just
boil.
accepted it.
Just boil, yeah. Okay, we would have to probably look at the initial conditions. Yeah.
Mine doesn't look exact.
So you probably have different, but it looks like ODE int, right?
Yeah.
Because you had different initial conditions, right? Than I do. So you might get a different curve depending on your whatever you set for the parameters, okay, of the boiling and baking, right? But as long as you get the same curve as ODE int, you're good.
So, you know, I was here last time. When I opened my computer, VS Code straight up was gone. Like, I had to reinstall VS Code, and my code that I had on VS Code from last time
Yeah.
was also gone. Is the code posted in Canvas?
No, I mean, there's one with gaps on Canvas that you'd have to fill in. So if you go on Canvas, there is one that has most of the stuff in it. But otherwise, your only other option is to just go and kind of just redo it with the lectures, follow through with the lectures. Yeah. Sorry about that. You know, computers can be weird. They're trying to control us. Okay, let us continue the lecture now. Okay. So that's great so far. These are the examples in the etc. Now, the other question, which some of your colleagues asked, could we apply the forward Euler method? Could we apply the forward Euler method to a system of initial value ODEs? Absolutely. You can apply it to a system of initial value ODEs. So now I want you to take this. This is the SIR pandemic model that we solved last time together with ODE int. So just like we did last time, now take the forward Euler formula and just apply it to each one of those equations. Just write it in this form. So Sn plus 1 equal Sn plus delta t, right-hand side of S, and expand that out. Do it for the infected and do it for the recovered. You'll get 3 discrete equations or 3 recurrence formulas for the forward Euler method for a system of equations. This is also a classic exam problem. Okay, if nothing else is going to motivate you to do this by hand, this should motivate you to do this by hand. Yes, this is a system. Why it's a system? Because they're coupled to each other. They're connected. The heat transfer with the oven versus boiling, this is not a system of equations. They're 2 independent. They don't depend on each other. This is a system here, right? As the equation on S depends on I, the equation on I depends on S. R is kind of just depends on I, but it's its own thing. Okay, but it's a system. They depend on each other. Okay, so go ahead and write the forward Euler method by hand, analytically. So express the forward Euler method for this system. What that means, expand this right-hand side. Tell me what it is. For S, it's minus beta over n, I times S. So put it in terms of the index notation for n, you know, for the time, what time level, etc. Okay? We did this last time with a single ODE. Do you have a question? Oh, yeah, yeah.
I can't see because I copied it down exactly and I can't see what the problem is.
What is your T end? Oh man, you're combining all notebooks together. All right, so let's kill the kernel. Let's restart. Okay. Okay, we can at least, let's say, where we're starting from here. Okay, so at least we got this, right? Okay. Now we can go for this one. Let's see. Okay. Go. Yeah. Probably. So that's yeah. Having these master notebooks for different problems combined together, I wouldn't recommend that. Okay, let's see. You got something? No?
Are we doing 3 like Eulers at the same time to do this?
Of course, yeah. It's just like you applied it to a single equation. It doesn't take. It's 3 lines. It's a 3 lines. Dude, it's 3 lines.
Oh, I thought you wanted us to write out like the. Oh, okay.
Unless
I thought you wanted us to write out like every step, like S1.
no, but that's the recurrence formula. You write it as Sn plus 1 in terms of Sn. That's what I want. Just express it Sn plus 1 in terms, and In plus 1 and Rn plus 1, okay? So you simply take your forward Euler formula and apply it to each one of those equations, okay? Try it. Yeah, okay? Make sure you're clear on your subscripts, because soon it's going to get really messy, okay? And understand what those subscripts mean. N plus 1 is what you're trying to predict, is the new value, and n is the old value, which is something you know, something that exists. Yep. Yes. Yes. See, and then it becomes pretty easy, right? Yeah. And now the way to know that you can solve this is when n is 0, you have your initial condition, right? And you can start at S1 in terms of S0, etc., and then you move on, right? Okay. Oh. We'll talk after class. All right. This is what you should have gotten. It's simply applying the forward Euler formula to each one of those equations. For the equation for S, Sn plus 1 is Sn minus plus delta t times right-hand side at n, but the right-hand side is minus beta over n times I times S applied as at n. Everything is at n. I at n, S at n. Same thing for the infected. I at n plus 1 is I at n plus delta t times right-hand side at n. What is the right-hand side of I? Is beta over n I times S minus gamma I. You apply them at n, then you have In, Sn, In. Just put n everywhere. That capital N is the population size. The lowercase n is a counter for time, right? Beta over n, I mentioned last time that we needed to normalize that per population so that the infection rate doesn't is the same for any population size. It's just a property of the ODE system. Okay, don't worry about that. Will be given to you. Okay, the ODE will be given to you. All you have to do is discretize it. Okay, yeah, beta over n is constant. Don't confuse this capital N with the lowercase n. Okay, n here is a subscript. It's an index. It's a counter. All right. Okay, so once you have these formulas, that's the first thing you need to do when you're faced with a problem. Again, you're on an airplane. You need to solve a system of ODEs by hand, right? And that classic example. So you write that recurrence formula first, okay?
So essentially, on the ordered Euler method, we are getting back like a bunch of data points that are solutions, essentially. So
At the different time levels. Yep, at the different times.
so then we could use, if we wanted like the equation solutions, we could use something like cubic splines or something to interpolate.
No, you don't do that.
No, you
Nope, nope. Yeah, you don't do that. I mean, if you want a formula, you know, yeah, I guess you could do that, but that's rarely the purpose. Once you have the discrete data points, you know, getting to that level is just enough in and of itself. But you could do that if you want a formula that you can use and apply, sure, but, you know, yeah.
For the second one, if the pi wasn't there and it was just the constant gamma, would you still put the delta t?
Yeah, because the delta t multiplies the entire right-hand side. That's a good question. Yeah. If you look at the formula above, delta t multiplies the entire right-hand side, whether the right-hand side depends on phi and t or not. If it's a constant, the right-hand side, yeah, it needs to be multiplied by delta t. Okay? All right. So now that you have these recurrence formulas, now you can take some steps given initial conditions and all the parameters, okay? Take a single time step. Just take me from the initial condition t equals 0 to t equal 2 days, and take a single time step of 2 days. Now this ODE is in days, okay? So d by dt, that unit of time is days, so you don't have to do any conversion, okay? Delta t is 2, okay? So just take a single time step like we did last time with the single ODE. We did 4 or 5 time steps. Right now, you're just going to do a single time step. You have the initial conditions, and you have all the other parameters, beta, n, gamma, and delta t. So now you will get numerical values, okay? If you need paper, I have some paper this time. Yeah, so those are the initial conditions, 0, 0, 0, right? That's even better.
So in this case, we're assuming that n is equal to 0 and n plus 1 is equal to 1.
Yeah, so you always start at 0, right? At n equals 0, and then the next step is you take one step, so it will be 1, right? That's correct. So you would be trying to find S1, I1, and R1. Once you have those, then you find S2, R2, and I2. Just like we did with, it's the same procedure as the single ODE, okay, that we did last time. You probably don't remember that, but once you review, it should click. Yep. It's just formulas with symbols. You substitute the parameters, and you can get new numbers. So you're starting from the initial condition at I0, S0, and R0, and you're trying to predict that next just one time step out. And when I say one time step, that's T0 plus delta T. Your delta T is 2 days, so you're predicting what happens in 2 days. That's it, one time step. And the ODE, the units of time are days in the ODE, so you don't have to do any conversion for delta T or anything else. Okay? Okay. You asked that question last week, right? So you asked that question last Thursday if we can apply it to a system. Yeah, this is it. Yep. Yeah. Yeah, now each one of those values, well, that's technically not correct. This is S1, I1, and R1, right? That's what the first time step, right? So now that is equivalent to Si and R at t equal t0 plus delta t, which is 2 days, right? So, yeah. Okay. So most of you got it. You just simply evaluate. You're taking the first time step. So you're starting at the initial condition at t equals 0, I0, S0, and R0. You take a single time step. That's going to take you to the next value, which we call S1, I1, and R1. Those are the values of the solution at t0 plus delta t, which is t0 is 0, delta t is 2 days. So that's what happens after 2 days of infection spread. Then the number of susceptible is 7.2. The number of infected is 2.7. And the number of recovered is 0.1. Okay? Those are actual numbers you will get even with ODE int. Okay? If you were to run this with ODE int and check at this time level, this is what you will be getting. Okay? Now, the meaning of those is that this is a single time step. If I were to ask you take, with a delta t equal 2 days, find what happens at 4 days. So you'd have to take 2 time steps. You start from 0 to the first delta t, and then to the next delta t. Because I told you that delta t needs to be 2 days. Okay? If I ask you what happens at 4 days with a delta t equal 4, it will be a single time step. Right? If I ask you what happens at 4 days with a delta t equal 1 day, you'd have to take 4 time steps. Tick, tick, tick. You can't, even if you jump, if you say, oh, yeah, I'm trying to find S at S4, for example. Well, S4 is going to depend on S3. S3 is going to depend on S2. S2 is going to depend on S1, which is going to depend on S0. So you have to do the calculation all the way back to S1 anyway. Okay? So instead, you start from S1 and then S2.
What about 4 days, but delta S is 3 days?
Delta t is 3.
T is 2 days.
So then that data point doesn't fit. You would have to find it at the next data point and do an interpolation in that case. Or you would do adaptive time stepping. You take a time step, which is beyond what we're doing here. But it's not unusual to say, oh, for the first time step, I'm going to take 2 days. But then somehow you estimate your error, that you have a bad error, then you shrink your delta t to half a day, right? So you can adapt your time step as you go. Okay, that time interval doesn't have to be fixed. Yeah, but we made it fixed because this is a 2000 level course, okay? I'll have a revolution on my hands if I went with adaptive time stepping, okay? Okay, implicit time integration. So far, we covered what we called explicit time integration. And I told you that I will define what I mean by that at the right time, pun intended, time integration. So I'll define that at the right time. And I alluded to explicit time integration a little bit in that. Notice how simple, relatively simple it was to compute the solution. Because the solution at n plus 1 only depended on the solution at n which you knew. So you could algebraically immediately solve for the new state of the system using whatever previous state existed. There was no fancy nonlinear solvers or linear systems of equations or any of that. You just evaluated the quantity, the function at the new time level using existing data. However, there is another way to integrate these systems motivated by something very unusual that happens with the forward Euler method and, for that matter, all explicit methods. So the forward Euler method is one type of an explicit method. It's the simplest explicit method. By explicit method, we mean that the solution at the time level is exclusively dependent on the solution at the previous time level. So you could just evaluate it algebraically immediately, okay? All right, so let's first go through some motivation for why we need implicit methods. And now what I want you to do, I want you to consider, or I'd like you to consider, this differential equation, d phi by dt equal minus 1,000 phi. Okay? And with an initial condition, phi at 0 equal 1. The exact solution looks like this. You have a sharp decay in a very short period of time, and then it just asymptotes and flattens out for eternity. Okay? Now, I want you to solve this ODE using the forward Euler method routine that we just developed. So you have to go back to that lobster example, copy the forward Euler code, put it in a new notebook, create a new right-hand side for this ODE, and try to solve this ODE with the forward Euler method on the interval 0 to 0.1. So your t end is going to be 0.1. And do a delta t of 0.03 seconds. And plot your solution. Let's see what you get. So your right-hand side is pretty simple here. It's minus 1,000 phi. So do it like we did the right-hand side for the convection or the baking, for the boiling or the baking. So again, we're going to try, not ODE int. ODE int will get this correctly. But what we want to try is use the forward Euler method that we just learned about and we implemented. We want to use our own routine in Python to solve this ODE with t end equals 0.1 second and time step 0.003 second. So get your notebooks. I'd like you to at least get started with it. So all you need is a right-hand side definition to solve this problem. That's all you need, just a right-hand side definition. Okay. I'm going to create a new motivation for implicit or methods with Professor Saad 2023. Okay. So what I'm going to do, what I'm going to do is copy this. I'm going to copy the boilerplate. Okay. And I'm going to copy our subroutine for forward Euler that we just created. I'm going to execute it. And now we need a right-hand side definition for the function that we looked at. Let me show you the slides. Okay. One moment. Okay. So that's our ODE. It has a sharp transient in it, so I'm going to call it RHS transient, okay? And that RHS, because here in our routine we assume the right-hand side goes phi t, so I'm going to give it phi and t over here. So I'm going to do f and t, and I'm going to return minus 1,000 times f, right? That's our right-hand side, minus 1,000 f. Agreed? Bless you. Bless you. Okay. So now we're going to do t end is equal to 0.1 seconds. Right? That's what I asked you to do, 0.1. And my delta t is going to be 0.003 seconds. Then we're going to call forward Euler. Forward Euler. We're going to give it the right-hand side transient. We're going to give it an initial condition f0 equal 1. So we'll give it an initial condition of f0, t end, and delta t. And we plot. What do you think is going to happen? Time sol. I'm going to do I'm going to do dash, oh, okay. Oh, look at that. It's nothing like the actual solution of the ODE. It's nothing, it's pretty cool though, right? But it's nothing like it. It's actually insanely large. Look at the y-axis. It's 1,000 million. It's a billion. Right? That's how I explain numbers to my son. So, 10 to the 9, I tell him 10 to the power 9 is 1,000 million. I'm like, why are you telling him 10 to the 9? What's left in life to learn anyway? So, it's incorrect. It's 100% incorrect. It just blew up. We say that the solution became unstable. Okay? What is the reason? We'll shed some light into that in a minute. But how about we reduce our time step size a little bit? Let's go to 0.02. Okay, so now it's unphysical, but it's at least bounded between -1 and 1.
How did it change that much?
It changed that much because of the dynamic behavior of these ODEs, right? So now remember what I told you about the choice of your time step size. Your time step size needs to be able to capture the fastest thing that's happening in your system. Okay? So if you look at this exact solution here, something is happening really there's a huge change happening really, really fast within probably 10 to the -3 seconds and less. So to be able to capture this drop over here, we need our time step size to be smaller than how fast this drop is occurring. Okay? So let's shrink our time step size a little bit more. Go to 0.001. Oops. Okay. Now we got something. Okay? Now if you shrink it more, 0.5, keep cutting it in half. Okay, we're starting to capture the solution better and better. Okay? Now this happens, yes, Ethan. Well, that was gonna be my next point. So now there's threshold. Remember the interaction between h and round off errors. There's a point below which, after which, if you keep shrinking your time step size, your round off errors are going to actually dominate your error, your total error. So that becomes a problem. But worse than that is, look, in this interval, you have 1, 2, 3, 4, 5, 6, 7, 8 data points, probably, just in this interval. But in this entire range where nothing is happening, it just goes flat. We probably have 1,000, 10,000 points over here, which are doing nothing. They're just constant. So you're spending a lot of cost at solving this ODE with such a small time step because of this transient, and yet you're using that same time step everywhere. Well, there are ways to work around this by doing, okay, in the sharp transient region, we're going to go very small time step, and then in the outside the transient region, we're going to go larger time steps. But how do you know? How can you tell that? How do you adapt to that? There are methods that can do that, a little bit advanced, quite advanced actually. But the point I want to drive home here is actually the idea that the forward Euler method can be unstable, and even if you try to stabilize it with a very small time step, it becomes ridiculously costly. Now you might say, this is this one ODE, Dr. Saad, who cares? Well, come tell the researchers in my lab who are still running a simulation with a very small time step. It's taking them 1 month and they need to graduate next semester, right? So doing this is inefficient and not good, okay? So we need other methods. And I'm going to explain to you one method that circumvents this issue. And first, I'm going to give an explanation of why this happens for this particular ODE. Okay, so we're going to consider, so remember we had d phi by dt was equal to minus 1,000 phi. Okay? So now I'm going to turn this into d phi by dt equal minus some constant times phi. A could be 1,000, could be 5, could be a billion, doesn't matter. Okay? And with an initial condition of phi 0. Now, we know from the exact solution of this ODE, this is exponential decay. Okay? So numerically, if we're starting with an initial condition, or any condition, any initial condition, the next value we predict, by definition of this ODE, needs to be smaller than the previous value. If it's larger, then you're going to go unstable. That's going to be our definition of sanity, if you want, for this, for the forward Euler method on this ODE. So here's what happens. If you apply the forward Euler method on this ODE with a time step size of h, you get phi n plus 1 equal phi n minus ha phi n. Agreed? So that's phi n plus delta t times right-hand side at n. The right-hand side is minus a phi. Okay? So this is what you get. Phi n plus 1 equal phi n minus ha times phi n. You can combine those on the right-hand side. You get phi n plus 1 equal 1 minus h times a. A is that coefficient. H is the time step size times phi n. Now, for this ODE, our condition for stability is that phi n plus 1 is smaller than phi n. Because by definition, this ODE is an exponential decay. ODE is decaying. So starting from any point on that ODE with an initial condition, the next value needs to be smaller than the previous value at a minimum. That's a condition for the solution to at least converge in the right direction. So if you impose this condition that you want phi n plus 1 to be less than phi n, then the absolute value of this coefficient 1 minus ha needs to be less than 1. So that strictly puts a condition on the time step size, on h, that for these types of ODEs, your time step value cannot be anything. It needs to be less than 2 over a. If it's less than 2 over a, you can at least guarantee that you're not gonna, your solution is not gonna wildly oscillate. It's just gonna stay and satisfy the rules. But the cost of that is that if you have sharp transients and then regions of slow change, you're paying the price of a very small time step, which is a very expensive price to pay in the grand scheme of things. This is where implicit methods were invented. If you remember last time, I told you the forward Euler method is like you're driving your car and looking in the rear view mirror, right? And this is why. This stability issue is why that happens. If you remember with the forward Euler method, we evaluated the derivative, the slope, at n to predict the value at n plus 1. Okay? It turns out that that's the problem for this stability issue. So if you remember, the forward Euler method, which was a generic explicit method, we evaluated the derivative at time level n and did a forward difference, and then everything was at n, right? And you found the solution at n plus 1 using everything at n. With implicit methods, what we do is say, okay, no, we're not going to look in the rear view mirror. We're not going to evaluate the derivative at n to find n plus 1. In fact, to find n plus 1, we're going to look at the derivative at n plus 1. We're going to try to look forward. So now when you do this, if you try to evaluate the derivative at n plus 1, then your right-hand side becomes everything at n plus 1, right? Because that's the definition of the ODE, d phi by dt equal right-hand side. If you evaluate d phi by dt at n plus 1, then your right-hand side is at n plus 1. Now you take that derivative and approximate it with a backward difference, you get this formula. Phi n plus 1 minus phi n over delta t, which is the same as this one, but look at the right-hand side. This right-hand side is at n for forward Euler or explicit methods. This right-hand side is at n plus 1. And we call this an implicit method. Why? Because you have phi n plus 1 on the left-hand side and phi n plus 1 on the right-hand side. Depending on what r is, That is an implicit equation. We call this particular one the backward Euler method. And we write it this way. Phi n plus 1 is phi at n plus delta t or h times the right-hand side at n plus 1. So you're evaluating the future with information from the past and information from the future, but you don't know the information from the future. That's why it's implicit. Now we're going to figure out a way to untangle that information in the future, right? But that's the power of this. And you will see in a second now that for this ODE, d phi by dt equal minus a phi, with a positive, that this backward Euler method is always stable, whatever delta t you choose. So let me do this exercise with you together. So for the backward Euler method, this ODE turns into phi n plus 1 equal to phi n minus ha phi n plus 1. Compare that to the forward Euler method, which was phi n plus 1 equal phi n minus ha phi n. Okay, now we have phi n plus 1 here. Now when you combine the two and solve for phi n plus 1, remember our condition for stability was that phi n plus 1 is always less than phi n. And this is always true because h is always a positive quantity. And a was positive in this case. So this ratio is always less than 1. So this is always true. The implicit method and implicit methods in general are always stable, regardless of the time step size you choose. Doesn't matter. It doesn't matter. That's the advantage of implicit methods, because you're trying to predict the future using information from the future. Now that gets you into this kind of circular loop. We'll address that in a minute, but this is the power of it, is that you circumvented that stability problem. You don't have any restriction on your time step size anymore. Accuracy is a different issue, but if you use the backward Euler method on this problem, you're going to converge it with any time step, and we'll do this example together. But let me go back to this and try to figure out what it means to have information from the future on the left-hand side, and you're trying to predict the future with information in the future. Does this remind you of something we did before, like x equals sine x, right? Or x equals sine x cosine x? No. No. This is, in general, a nonlinear equation, right? Because the right-hand side, actually, I do have a question. So explain why this is, in general, a nonlinear equation. That's how we can predict the future with information from the future through nonlinearity. Why is this, in general, a nonlinear equation? So phi n plus 1 is what we're trying to find. So you have phi n plus 1 on the left, and you have r of phi n plus 1 on the right. R is the right-hand side. Could be anything. Shows up in a nonlinear fashion because r, in general, could be anything. Could be sine phi n plus 1. So you'd have phi n plus 1 equal phi n plus h times sine phi n plus 1. What is that? That's a nonlinear equation. We did this. Except now we just have an index called n plus 1. So at every time step, you have a nonlinear equation you need to solve. So that's why you need to have a fast nonlinear solver, because you embed it in a time-stepping routine. You solve it 1,000 times. And if each time you're doing 10 iterations, that's 10,000 total calculations, you know. And you can write this, in general, what we do, remember, we write everything in residual form. You move everything to the left-hand side or to the right-hand side. And this would be your residual function. This is very important, because I guarantee you're going to get a problem like this that you have to solve by hand on the exam. I can tell you from now, you are getting at least one of these problems, okay, that you have to solve by hand. As far as I'm concerned, this is just a nonlinear equation. It just looks a little bit differently, but it's a nonlinear equation. Yeah, but this is the definition of the residual equal to 0, right? Yeah. So now our residual function is phi n plus 1 minus phi n minus delta t times the right-hand side at n plus 1. And the beauty of this is that now you can write this for any right-hand side. You can write the backward Euler for any right-hand side. Yeah.
How many unknowns did you have in that? Just one?
What do you mean? Like?
You know when you have a residual equation, you have if you have two unknowns, you need two equations.
Yeah. So if you have a system of nonlinear ODEs, you would have a system of nonlinear equations here.
So this
Yeah.
equation alone only has one.
Yeah, that's for a single ODE, right? Because we didn't learn how to do by hand a system of nonlinear equations, so I will not show that. But once we hit boundary value problems, we actually did a system of nonlinear ODEs with the heat transfer problem. We're going to revisit it again. But yeah, this is the equivalent. If you remember, that's actually a good point. So if you remember with the heat transfer problem, one example we did with nonlinear systems of equations, okay, with the heat transfer problem. This is the equivalent of it, but for time. And this is a single equation with a single unknown phi n plus 1, right? So now you take this, you start at 0 to advance to 1, you iterate this one however many times you like, and then you find phi at 1, and then you move to the next level. So in every time step now, you have a nonlinear solver that needs to solve this nonlinear equation, okay? So I have an algorithm here for the backward Euler algorithm, backward Euler method. We will implement it together. So you would first need to guess what your phi n plus 1 is. And remember, you always ask me, like, how do we start our initial guess for a nonlinear solver? And I said, typically, these nonlinear solvers are part of time-stepping solutions. So you use the previous value. So you use the initial condition as your initial guess for the nonlinear solver. Then once you find the solution, you use that solution as the seed for the next solution, and so on. Okay, so you don't have to worry about initial guesses anymore. And then you just use Newton's method to solve the residual for the residual function, and then you update and keep going and keep going. So there's two loops. There's the outer loop that takes you in time, moves you in time, and there's the inner loop that within a time step converges the nonlinear solver or the nonlinear equation. So here, next, we're going to combine fsolve with the version of the forward Euler method, okay? But first, I'm going to do an example by hand, and I'm going to have to guide you through this, but I really ask you to study this very carefully at home. So, go through it over and over again. Make sure you can reproduce it independently without looking at the slides. So now suppose you want to solve this equation. That's a second-order reaction, let's say, for some concentration field. dC by dt equals some minus alpha c squared. And with an initial condition of A, capital A, call it. Now, I can tell if I use a backward Euler method, an implicit method, because the right-hand side has a squared in it, I'm going to have a nonlinear equation, okay? So if you apply the backward Euler method to this, you get Cn plus 1 minus Cn over delta t equal minus alpha times the right-hand side at n plus 1, right? So that's minus alpha times Cn plus 1 squared, okay? So now you see the nonlinearity. Now, you could say, oh, Professor Saad, this is a quadratic. I can solve it by hand. Exactly, yeah. We're not doing that exactly right now. We need to do that with a Newton method, okay? So if I ask you to do Newton's method in the exam, you do Newton's method, okay? Then you create your residual form. So in this case, I move everything to the left-hand side. So you get Cn plus 1 minus Cn plus alpha delta t times Cn plus 1 squared, okay? Now, in a minute, the indexing is going to get quite complicated. For Newton's method, you also need the derivative of the residual function. So that tells you for the final, yeah, you need to know Newton's method, okay? You need to know it very well, okay? Now, you differentiate with respect to the variable of interest, which is what? Cn plus 1, right? So for all I care, you could call Cn plus 1, call it x, Okay? Just call it x if you want, if you get confused with all the nomenclature. Okay, just call it x. That's your variable of interest that you're trying to solve for. Okay? Then your derivative, residual derivative with respect to Cn plus 1, you just differentiate with respect to Cn plus 1. The last one, minus Cn, doesn't matter. That's Cn. That's a constant. That's a value from the previous time step. Okay? You know that. So it doesn't have, its derivative is 0 with respect to Cn plus 1. Now you do your Newton update. Okay? Here's the explosion in indexing. Trust me, this is nothing compared to what we deal with. We have usually 7 indices we're dealing with, 5 to 7 indices we're dealing with between time and ijk in space, and like 2 internal iterations we have to keep track of. But at least now you have to deal with 2. Remember, we're solving for Cn plus 1. So if C at n plus 1 was called x, then that would be just x, okay? But now we have the Newton iteration, which we follow with a subscript k, okay? So now Cn plus 1 at k plus 1, that's the new iterate, is a function of the previous iteration, k, right? Minus r at ck over r prime at ck. All of those are at n plus 1 because now we're trying to find n plus 1. We're trying to find Cn plus 1. So we're fixing that superscript, but we're changing the subscript. So you can see here, if you go from 0 to 1, you're trying to solve for C1, C at T1, okay? Then you have to iterate this over k until you reach convergence, and then that would be your answer. Then you start to compute C2. You fill in the gaps here for r and r prime, and you get this complex recurrence formula for this example. Each problem is going to have its own residual function, okay? And you iterate this until convergence per time step. This is going to happen every time step. So if in the homework I ask you do time steps, 2 time steps, and 3 iterations per time step. So you take the first time step, and that first time step you go from k 0, 1, 2, and then you move to the next time step, do k 0, 1, 2. Okay? All right, so let's see how this might work with an actual example. If alpha is 0.25 and delta t is 0.5, and my initial condition is C0 equal 1, at n equals 0, so this is the recurrence formula up there, then at n equals 0, we're trying to predict C1. Okay? So now we fixed the superscript, right? This is the first time step. We're trying to get from C0 to C1. Now, C1 is a nonlinear equation, right? So you have to iterate it over k. So that's where you see C1 k plus 1 is C1 at k minus alpha delta t C1 at k squared plus C1 at k minus C0, that Cn over there is just a constant, comes in from the initial condition, over to alpha delta t ck at 1 plus 1, okay? Now, what is your initial guess for the nonlinear solver? You use the value from the previous time step, which in this case is your initial condition, C0. Okay, that sees your initial guess. Then you start iterating. The first iteration, okay, so C1, 1, right, is C0 at 1, okay? So that's k equals 0 here, okay? So we're doing ck plus 1 is ck. So you plug in the values and you get a number, okay? Now that gives you the first iterate, C1. You use that to improve your guess. You go to C2. Now, k is equal to 1 here. So this would be ck plus 1, which is C2. And you continue all the way. Our objective, remember, is to find C1. We're going to continue iterating until we converge. And once you converge, okay, that's the number for convergence in this case. Now, in the homework, I'll ask you to do 2 iterations, okay? Because it might take 50 iterations to converge. That's a programming problem. But by hand, I'll ask you to do a couple of iterations. Now, once you've converged, you drop the subscript. That's C1. That's the value of the dependent variable, concentration in this case, at T1. That's T0 plus delta T. Now we're at T1. We're going to move to T2. Okay? We do the same thing. Now n equal to 1. So now we're trying to predict C2. Yes? Yes, you have the outer loop, which is your time loop, and the inner loop per time step you're iterating. So you got it. It's just, this is exactly what it is. You have an outer loop that takes you over time, moves you over time, and an inner loop within each time step you iterate. Okay? This is very important. Okay? I cannot stress this enough that you need to master this. Okay? It's just a lot of indices. It's annoying. You do this example twice, and you got it. Okay? So now we are solving for C2. You could call C2, it's not C squared, it's C2. Call it X, okay? So now you have xk plus 1 is xk minus alpha delta t. And you know how to do this. We did it with Newton's method. You all did it on the exam. So I know you can do this, okay? And again, we iterate. So now we're trying to find C2. We start with the first iteration using C0. What is our initial guess for the iteration? It's going to be the value from the previous time step, right? So you don't have to worry about initial guesses. Use that value from the previous time step, and you iterate. And same thing. And in fact, you converge pretty quickly in this case. Because it's a quadratic, it gets it in two, 3 iterations. And then once you've converged, now that becomes your C2, and you start it again. Okay? Repeat again. I can change this right-hand side 1,000 ways. I can put sine c squared. I can put square root of c. Okay? All of those follow the same strategy. Let's use the exact derivative. Yeah, because that complicates things even further when you use a discrete derivative. Okay? Okay. So let's do this in Python. I'm going to try now to implement the backward Euler method and solve this problem in Python. Okay? And we will be done with initial value problems. Okay. So for the backward Euler method, I'm going to call it define. I know it's like sunny outside, end of the semester. You don't want to focus, but this is very important material. Okay, because every ODE you're going to see moving forward is going to be a nonlinear ODE. ODE int is going to solve it for you, but when it does not, you're going to see a few times where it cannot solve it for you. You have to do your own. You have to investigate on your own. And this is the material that will get you there. Okay, so we're going to do backward Euler. And for the backward Euler method, again, we just need a right-hand side. Same thing as the forward Euler method. An initial condition, a end time, and a time step size. Okay? Now, just like the forward Euler method, in fact, I'm just going to copy everything from the forward Euler method, and I'll show you where the difference occurs. I copied everything from the forward Euler method. Okay? Except that here, this equation is not true over here. This is only for the forward Euler method. It's explicit. It's kind of nice and easy. You just evaluate the quantity at n plus 1 in terms of everything at n. For the backward Euler method, we have that nonlinear equation. So we need to solve a residual function. So what we would need is something like fsolve, and then let's say residual, or backward Euler residual. Okay, and for fsolve, you also need an initial guess, okay, which is going to be our value from the previous time step. Okay, so what is the value from the previous time step? Is f at n. Okay, if you remember fsolve, we gave it at a minimum a residual function and an initial guess. Now we haven't defined the backward Euler residual. We're going to define it in a minute. I'm just kind of trying to put pseudocode over here. Okay, I'm just trying to put some pseudocode over here. Okay, so let's go ahead and define the residual for the backward Euler. And this is a general backward Euler residual. You can use it with any right-hand side function. Because when you look at the slides, the backward Euler residual, where is it? It's general. Doesn't say anything about any ODE. It's always phi n plus 1 minus phi n minus h times a right-hand side. So this residual function just needs a right-hand side. And it's a very generic residual function. Okay? So let's declare it over here. We're going to define backward Euler BE residual. And what is it going to need? It's going to need phi n plus 1, phi n, delta t, and a right-hand side. Agreed? And the time at n plus 1. What do we need to implement this residual function? We need phi n plus 1, phi n, delta t, the right-hand side function, and tn plus 1. So we'll just implement those over here. We just say, okay, residual function is going to need phi n plus 1. Let's call it fn plus 1. And it's going to need fn, or let's say right-hand side. The right-hand side function is going to need fn. It's going to need the time step size, which is h, or delta t. And it's going to need tn plus 1. Right? I'm not inventing anything here. I'm just trying to reproduce this function.
So what are we solving for?
You're solving for phi n plus 1.
We still need to put it. Okay.
Yeah, we still need to put it in residual form, right? So that will circumvent the our doing our own Newton method, right? And all I need to do is return phi n plus 1 minus phi n minus delta t times right-hand side phi n plus 1 and tn plus 1. Guys, it cannot be any simpler than that. Look at this. This is exactly, if I do this, I'm returning this. I'm not change. I just swapped the order for these because we did everything right-hand side of phi and t. But that's it. I'm returning. If the residual function is given phi n plus 1, phi n, delta t, right-hand side, and tn plus 1, it's going to compute something. It's going to compute the residual. So that's what fsolve is going to provide the residual function with, right? Just like we did with fsolve before. Okay? All right. So now we go to fsolve. Okay, we're calling a residual function. That residual function needs a bunch of arguments. So we're going to pass them as, so if you look at fsolve, which we need to import from scipy.optimize, import fsolve, right? Okay, if you look at the function signature for fsolve, it can pass a bunch of arguments to your residual function. That's what we're going to pass. We're going to pass right-hand side fn, delta t, and tn plus 1. Because by default, the residual function always takes fn, the phi quantity that we're solving, the nonlinear variable, right? So we're going to give it args. Args equal right-hand side fn, delta t, and fn, and sorry, tn plus 1. Okay, what is tn plus 1? Well, simply tn plus 1 is time at n plus 1, which we already declared. Okay. Now that's our solution. And then we place that solution under fn plus 1. Okay. Okay, so now let me see if this is going to work with this ODE. We're going to be doing backward. So we're going to do time and solution. Sorry. You see what I did here? Yep. Backward Euler is equal backward Euler method. Okay, we're going to give it a right-hand side function, which is right-hand side transient. Okay, we're going to give it an initial condition. We're going to give it t end and dt. Okay, so let's make a challenge here, and let's make dt equal 0.003, which was the one that diverged with forward Euler. Okay, I know you're still typing, but I'll give you a minute. The right-hand side? Oh, that's, okay. So that's way up here. Sorry. Okay, so let me know where you want me to scroll to. So I'm going to solve this again with the forward Euler at that bad time step size, 0.03 seconds, okay? But now I'm going to solve it again with that 0.03 seconds, and t end is 0.1, okay? 0.1, and f0 is equal to 1, okay? And then plt.plot time sol. Oh, look at that. Even with the worst time step, we said that the backward Euler method is unconditionally stable. Whatever time step we choose is going to converge to a solution. It's not going to diverge. It might not be accurate. Okay, it might not be accurate, but that's not the question we're trying to solve here. Okay, so let's do 0.01. Look at that. Even with 0.01, okay, you're way behind. Most of you are way behind me. Okay, let's see. You got it? Okay, so what time step did you use?
0.003?
Yeah, this isn't right.
Yeah, that's what I was
Backward Euler.
Well, yeah, I just defined
Oh, backward. Okay, RHS. Okay, and then fsolve. Oh, you need to save your solution, right? So okay, don't forget to save your solution. So fsolve is your Newton solver. It does the iteration internally and returns phi n plus 1. We're just going to store it here, okay? Okay. You're not going to leave until you get this. Okay, look at you. Change the time step size now. Go higher, and it's still going to be stable. There we go. No? Oh. Okay. Okay. Yeah, so scroll up to the function. Yeah, so you need to store your fsolve into fn plus 1. So you could put f bracket n plus 1. Yep, equals, yep. Yep. So ODE int is doing all of this behind the scenes for you. But you kind of don't know what it's doing. Okay?
So if this is the same thing ODE int does, why does ODE int sometimes not work?
There might be cases where it doesn't work, or you need more control over what it's doing. You need some specific adaptive time stepping, and then ODE int becomes not very useful.
Says my TNP went, so my TN plus 1.
Yeah, it's not defined. So you have to define a new variable here. Yeah, this one. This one. I kind of did it backwards, right? So I went to fsolve, and then I tried to figure out what I need for fsolve.
I mean, it still goes down. It's just not like accurate.
What is your? Yeah, that's not right.
Well, no, I changed the time step.
Even if I, what did you put? 0.03. Yeah. It's stable. It's not accurate. Yeah, but it's stable, right? What we mean by stable is that it follows the right it doesn't oscillate, it doesn't go out of bounds. Yeah, doesn't mean it's going to give you the right answer, okay? Whew, we finished implicit time integration, okay.